In this chapter, we'll be going over the basics of functions and their graphs. So starting with the definition of a relation is going to be any set of ordered pairs. And this is where the set of all of the first components of the ordered pairs is called the domain, and the set of the second components is called the range. So for example, if we have this relation right here, and we want to find the domain and range of it, you can see that we have all of these ordered pairs. We have 4 different ordered pairs here, and we have the squiggly brackets, the braces, which represent a set. So we have a set of ordered pairs. So if we want to find the domain, it's going to be all of the first elements. So all of those first elements that I underlined there. So for the domain, it is a set, so it's going to be a squiggly bracket. And it's going to be all of those numbers that I have underlined. So -1, 4, -3, and 8. And now for the range, it's going to be all of the second components here. So the range is 2, 0, 1, and 5. So we can extend this definition to functions. A function is going to be a relation such that each element in the domain corresponds to one and only one element in the range. So what this means is that for a function, no ordered pair has the same first component and a different second component. Each first component can correspond to only one second component. So taking a look at these examples right here, determining whether each relation is a function or not. So for the first one, for A, what we're going to do is look at all of the first elements. We have 1, 2, 3, and 4. And since none of the first elements repeat themselves, they're all unique, they're all different, that means that this is going to be a function. Okay, and then for the second one here, we take a look at the first components. We have 6, 6, 8, and 9. So taking a look at these first 2 ordered pairs, we actually have a 6 as both of their first components, and the one on the left, or the first one here on the left, is going to a second component of 1, and the next one is going to a second component of 2. So since we have the same value in the first component going to a different value in the second component, this is not a function. Okay, so that's one way we can see a function. We can see it as a relation or a set of ordered pairs. Another way that we're going to see functions, they're going to be written as equations. So for this example here, we have this equation which defines y as a function of x. So the equation is y equals 2x squared minus x plus 8. And we have our 2 variables, x and y. The independent variable is our x. We can think of this as the input value, and this can be assigned any value from the domain. And that leaves the other variable y here as the dependent variable. So essentially we're plugging in values of x that we're allowed to plug in based on what the domain is, and we're seeing how y changes with respect to x. And now bringing this back to the definition of a function, if we have an equation that's solved for y, and we plug in a value of x, and it gives us out more than one y value, then that means the equation is not a function. Okay, so let's look at a couple examples here. For the first one, we have x squared plus y equals 4. We want to determine if this is if it defines y as a function of x. So the first thing here, what we would have to do is solve this for y. So if we solve this for y, we would actually have to subtract x squared on both sides to get y by itself. So it's going to be y equals 4 minus x squared. So now we want to try to think about this. If we plug in values of x, is it going to give us out one y value or more than one y value? So in this case, when we plug in an x value, it's only going to result in one y value, which means that this is a function. For example, if we plugged in x equals 2, it would be 4 minus 2 squared, which is 4 minus 4, which is 0. So that gives us out 1 y value. Okay, for the next one here, we have x squared plus y squared equals 4. So solving this for y now. This one's a little bit more complicated. We start off by subtracting the x squared again. So what we're going to do here, which we have seen before, in order to get y by itself instead of just y squared, we have to take the square root of both sides. When we take the square root on the left, it cancels the squared. And on the right, we get plus or minus the square root of 4 minus x squared. So we have to remember that every time we have an equation like this and we're taking the square root of both sides, we're always going to get this plus or minus right here on the other side. So now when we plug in a value of x, let's say we plugged in x equals 0, that would be the plus or minus the square root of 4 minus 0, which is the square root of 4, which is 2. So we would get plus or minus 2. This is always going to give us two answers. It's going to give us the positive root and the negative root. So since it gives us more than one value of y for just one value of x, this is not a function. Okay, and then the last one here, we have y equals x plus 4. So this one's actually already solved for y, so we don't have to solve it for y. So this one, we have to imagine plugging in values of x. Every time we plug in a value of x, all we're doing is adding 4 to it to find the corresponding y value. This will always only give out one value at a time, so that means this is a function. Okay, so this brings us to the next thing, which is function notation. So up until this point, we've been using our dependent variable y as kind of like our name for the function. So instead of using y, we're going to essentially be giving our function a letter name, and the ones that we use most often are f, h, or g, but technically it can be any letter. So the notation for this is going to be f of x, and we read that just the way I just read it. We read it as f of x, and you can also think of it and should think of it as f is a function of x. F is the function where x is the independent variable. So we could also have something like g of x or h of x or something like that. I'm just going to be using f for now. So it's also really important to know that this f of x, that's not multiplication. That does not mean f times x. That is one set thing, and you can think of it, as I wrote up here, as the replacement for y. Okay, so let's start by evaluating these. So let's say we have the function f of x, which is x squared plus 3x plus 5, and we want to evaluate the following. First one, we want to find f of 2. So what this means is that we want to evaluate f of x when x equals 2. So what this means is that we're plugging in a 2 everywhere there's an x. So it's going to become 2 squared plus 3 times 2 plus 5. And then we just have to simplify this using order of operations. And this will give us 15. So kind of as a final answer, we could say f of 2 equals 15. It's also important to note here that this corresponds to an xy ordered pair. And the ordered pair would be x equals 2, and the y value is 15. So these are function values, which are also called, are also our y values. So the next one, f of negative x. So instead of having f of x, now we're going to plug in a negative x everywhere we see an x, and make sure you use parentheses. So it's negative x squared plus 3 times negative x plus 5. And then we have to simplify this. Negative x squared is the same as positive x squared. This is where we have to remember a negative x to an even exponent will just be positive x to that exponent. Negative x to an odd exponent will be negative x to that exponent with the parentheses no longer there. Okay, so for the second term, we have just minus 3x plus 5, and that is our answer. Okay, and then for this last one here, we have f of x plus 3. So taking a look up at the function, everywhere there's an x in our original function, we are now replacing it with x plus 3. So x squared becomes x plus 3 squared, and then plus 3x becomes plus 3 times x plus 3, and then just plus 5 for our last term. So what we have to do here is we have to expand out this first term. We have to FOIL this out. So maybe hopefully we can do that in our head. Let's do that on the side though. So x plus 3 squared is the same as x plus 3 times x plus 3. Foiling that out, we're going to end up getting x squared plus 6x plus 9. So just don't make the mistake of just squaring the x and squaring the 3 and that's it. Make sure you're distributing that out or foiling it out. Okay, so let's replace that in where that first term was. And for that second term, we're going to distribute the 3, so it's plus 3x plus 9 and then plus that last 5. And we're going to combine like terms here. And we get that f of x plus 3 equals x squared plus 9x plus 23. Okay, let's do a couple more here. We have f of x equals x cubed minus 2x minus 1. And for the first one here, we want to evaluate x, or f of negative 3. So x equals negative 3, so we're going to plug in a negative 3 everywhere there's an x. And remember to use parentheses. So order of operations here in evaluating this, we end up getting negative 22. So f of negative 3 equals negative 22. And remember, this corresponds to an xy ordered pair, negative 3 comma negative 22. Okay, next one for b, evaluating f of negative x here. We're going to plug in a negative x everywhere there's an x. And we end up getting negative x cubed minus 2 times negative x minus 1. So negative x to the third is the same as negative x to the third without parentheses because it was an odd exponent. Next term, negatives cancel to a positive, plus 2x, and then minus 1. Okay, and that is our final result for that one. Let's do one more example here. We have f of x is negative x squared plus 10x, and we want to evaluate f of 5 for the first one. So let's plug in a 5 everywhere there's an x. So we get this right here, negative 5 squared plus 10 times 5. We have to be a little careful that negatives on the outside. So 5 squared is 25, so this is negative 25 plus 50. Add those together, we get positive 25. Okay, and then for the next one here, evaluating f of negative x. Everywhere we see an x, we plug in a negative x. So we get negative x squared plus 10 times negative x. Once again, we have to be pretty careful here with that negative out front. Negative x squared is positive x squared, but since we still have this negative out here, that's going to remain where it is. So the first term actually ends up being negative x squared, and the second term is minus 10x. Okay, and last one, we have f of x plus h. So it looks a little different because we have this x plus h. We've done one that I believe it said x plus 3 on the last page. We do the same thing though. Everywhere there's an x in the original function, we're going to plug in an x plus h with parentheses. Okay, so it becomes negative x plus h squared plus 10 times x plus h. So we have to simplify this. That first term, we have to FOIL that out. So let's do that on the side. So x plus h squared is x plus h times x plus h. If we FOILed this out, we'd end up getting x squared plus 2xh plus h squared. And I'm going to plug that into the first term right here. we still have this negative out front, so I'm going to put the negative and then plop in that value that we just got. Okay, so now all we have to do is we have to distribute for both of these. So the first term becomes negative x squared minus 2xh minus h squared. The second term after we distribute that 10 is going to become plus 10x plus 10h. And then what we would want to do here is look to combine like terms. There are no like terms, so we're actually done. Okay, so for the next thing now, moving on to graphs of functions. So the graph of a function is going to be the graph of all of its ordered pairs, x comma y, in the rectangular coordinate system. So there's going to be different ways that we can graph things, graph different functions. For now, what we're going to be doing is we're going to plot several points and connect them with a smooth curve. So we're going to have values for x. We're going to plug those into the function, get out the function value, which is the y value, and that'll give us an xy coordinate. So let's do this example. Let's graph f of x, which is 2x plus 1. And let's start integers of x. Let's select integers for x, starting with -2 and ending with +2. So I have this little table down here, and we're going to plug in values of x from -2 to +2. So that's going to be -2, -1, 0, 1, and 2. And let's plug these into f of x. So let's plug in -2. So f of -2 is going to be 2 times -2 plus 1. That's -4 plus 1, which is -3. So that gives us the xy ordered pair, -2, -3. So we can actually plot that right now. That's right here. And let's plug in -1. And we get that f of -1 equals -1. So that gives us this coordinate, -1 comma -1. We graph that, plot that, it is right here. And then I'll just do the other ones quickly. So finding those other xy ordered pairs, we get all of these, and I plotted them over on the graph. So next we have to connect these with a smooth curve. So the way that we connect the points that we have is going to be a little bit different from function to function. This one ends up being a straight line. It's linear. Hopefully we can see that by the points. So we connect them. And when we connect them, make sure we have arrows on the end to indicate that it's going on in both directions indefinitely. And then we label it f of x as 2x plus 1. So the points that we found and the points that we graphed were just an aid for us to get the general shape of this curve. Technically, there's an infinite amount of xy ordered pairs on that line. Okay, so for the next thing is the vertical line test. If we have the graph of a function, or the graph of an equation rather, and we want to determine whether or not it's a function, we can't do the two previous ways that we did it, like when we did it to check if a relation was a function, and we can't do it to check if an equation is a function, because now we have the graph. But we're going to be using the same exact concept, that being no value of x can result in two or more different y values, and graphically speaking, this is the vertical line test. So the vertical line test says that if any vertical line intersects the graph more than once, it is not a function. Okay, so let's do these examples. Let's use this test to identify which graphs are functions and which are not. So the first one for A, all you have to do is either actually draw a vertical line or just imagine it, put a vertical line somewhere, and see if it intersects it more than once. In this case, if we put it anywhere essentially on this graph, it intersects it twice. Since it intersects it more than once, this first graph is not a function. Okay, and then the next one here for B, actually going back to A, for A, if we take a look at, say, this x value right here, it corresponds to a y value here and also a y value here. So that's kind of what the vertical line test is doing behind the scenes. It just means that x coordinate is corresponding to two different y coordinates in this case. So taking a look at B, if we draw a vertical line anywhere on this graph, so say we draw it right there, no matter where we put it, it's only going to intersect the graph once. That means this is a function. Okay, and the next one here for C. For C, if we put a vertical line somewhere, so I'll put it right over here. Clearly, no matter where we put it, it's always going to pass the vertical line test. So since it passes, that means it is a function. Okay, and then the last one for D, if we put a vertical line over here, we can see that it cuts through the curve more than once, fails the vertical line test. This is not a function. Okay, so relatively simple test here to determine whether or not a graph is a function or not. Okay, next we're going to be obtaining certain information from graphs. And we're going to be doing this by looking all the way to the left on the graph and all the way to the right on the graph. There's essentially three different options for these endpoints. We can either have closed circles, open circles, or arrows. If we have a closed circle at the end, or it could actually be in the graph also, a closed circle indicates that the graph does not extend beyond this point. It stops right there, and the point belongs on the graph. If we have an open circle on the graph, that's going to mean that the graph, once again, does not extend beyond that point. However, if it's an open circle, that means that point does not belong on the graph. And the last one here is an arrow. If we have an arrow on the graph, that just indicates that the graph extends indefinitely in whatever direction the arrow is pointing. So for example, if we have something like this, we can see that there is a open circle on the left and an arrow on the right. So that means the graph stops at -2, 3. And it is not part of the graph. It gets infinitely close to it, but it doesn't get there. And then over on the right, we have an arrow. So that means it's going to keep on going in this direction. We just obviously don't have to keep drawing it. The arrow indicates that it goes indefinitely in that direction. Okay, so for the next thing is going to be getting into notation for intervals. So there's going to be two ways we represent an interval. There's going to be interval notation and set builder notation. So for interval notation, it is unfortunately going to kind of look like an XY ordered pair. We can either use parentheses or we can use brackets. If we're using parentheses, so for example, if we have this right here, I'm just using x1 and x2, that means the interval is from x1 to x2. And since there's parentheses on the end, that means those endpoints are not included. For brackets, if we're using brackets, so it looks pretty similar, we have the interval x1 to x2. If we have brackets on the end, that means those endpoints are included. And some things we have to remember, the smaller number is always going to be first, and parentheses are always going to be used for negative infinity and positive infinity. For set builder notation, I'll be mostly using interval notation. For set builder notation, the elements are going to be described, but they're not necessarily going to be listed. So we'll see in an example in a little bit. We're going to have the normal set builder notation setup. It's the set of all x's such that, and then description of x values. So description of x values meaning something like x is greater than 4. Okay, so here is kind of the generic setup of all possibilities that we could see. The left column represents the interval notation, middle column is set builder notation, and the right column is the number line for the graph. So notice that on the graph on the right here, this graph is using parentheses and brackets. The way that I like to do it is I like to use open circles for parentheses and then closed circles for the brackets. So just keep that in mind going forward. Okay, so just taking a look maybe at these first two just to get an idea. If we have the interval a to b, so what that means, it's like on the number line, it's the interval from a to b, but it's not including a and it's not including b. In set builder notation, it would be the set of all x's such that x is between a and b. So notice it's always going to be less than sign when we're doing it in this notation for between two numbers, not including the infinities, and it's not or equal to because we're using parentheses. So for the next one, if we have the interval a to b and we're including the endpoints with the brackets, set builder notation, it would be x is between a and b. This time it has the or equal to because we're including the endpoints. Okay, and then maybe just skipping down here to one of the infinity ones. If we have from a to infinity, then that's when we can just write it as x greater than a. And notice on the number line, there's an arrow going to the right because it's everything greater than it and going to infinity. And then something like this one right here, negative infinity to b. That's x less than or equal to b because we're including b. Okay, and then one special case here is just if we have negative infinity to infinity, that just means it is the set of all real numbers. Number line, there'd be two arrows on both ends. Okay, so let's do a couple examples converting between the two to make sure we're comfortable. So for these first ones, let's express the interval, which is in interval notation. Let's express it in set builder notation, and let's also just create a little sketch of a number line and graph the interval. So we have the interval from 1 to 6, not including 1, but it is including 6. So it would look like this in set builder notation. The set of all x's such that x is between 1 and 6. And just notice that we're not including the 1, so there's no or equal to. We are including the 6, so there is an equal to. Okay, so on a number line, it would look something like this. So obviously just a really crappily drawn number line here. It's everything, it's the interval between 1 and 6, not including the 1, so we have an open circle, and it's including the 6, so we have a filled in circle. Okay, next one, we have negative infinity to 5. So for this one in set builder notation, it's going to be the set of all x's such that x is less than or equal to 5. So notice that I didn't write it like this. We don't need to include that infinity when we are using set builder notation. It kind of looks silly, so we just have to write x less than or equal to 5. Okay, and then on a number line, it's everything less than 5 and including it, so close circle and then arrow to the left. Okay, last one here, we have the interval -3 to infinity, not including -3. And just notice on these infinities, there's the parentheses as there always should be. So in interval notation, or rather in set builder notation, it's going to be the set of all x's such that x is greater than -3. And on the number line, it's everything greater than -3, so there's an arrow to the right saying that it's going to infinity. And there's an open circle at -3 because it was not or equal to. Okay, so let's go the other way. We have, starting with set notation and going to interval notation. So we have the set for a here, the set of all x's, such that x is between 3 and 8. We are including 3, we are not including 8. So in interval notation, we would have a bracket on the 3 and a parenthesis on the 8. And on the number line, it would look something like that, everything between 3 and 8, including the 3, not including the 8. Okay, next one we have the set of all x's such that x is less than -3. So less than -3 means it's going to go from -infinity to -3, not including the -3. And on the number line, it would look like this, arrow to the left indicating it's going to negative infinity, all the way up to -3 with a open circle. Okay, last one, we have set of all x's such that x is greater than or equal to 5. So greater than or equal to 5 means it's going to be everything greater than 5. So that's going to be 5 to infinity. And this gets a bracket on the 5 because we're including it. And on the number line, it's going to be an arrow to the right of 5, including the 5, so it gets a filled in closed circle. Okay, so this brings us to the last thing for this section. It is identifying domain and range from a function's graph. So we can use whichever one we want now that we know how to convert between interval notation and set builder notation. I'm going to be using interval notation. So we already know that for the domain, it's the set of all the first components in an ordered pair. The first components are the x values. So domain is going to be the set of the x values, or the inputs, and this is going to be where the function exists in regard to the x-axis. And since for interval notation and set builder notation, we go from smaller number to larger number, on the x-axis, to go from smaller to larger, we go from left to right. So we're going to be scanning these from left to right to find the domain. And then next for the range in the relation, finding the range of a relation, is the set of the second components, which is the set of the y values in an ordered pair. So the domain is the x values, the range is the y values, or the set of the outputs, and this is going to be where the function exists in regard to the y-axis. And since the y-axis gets larger numbers from bottom to top, that's the way that we're going to scan this to find the range. Okay, so let's do these several examples here. So let's find the domain and range of both of these, and I'm going to be using interval notation. So this first one for A, let's find the domain. So just denoting this with capital D and R for domain and range. So scanning left to right, we're going to be seeing where the function starts existing in terms of the x-axis. So it starts right here, and that's at x equals -2, and it ends right here, which is x equals +1. So it's going to go from -2 to 1, and there are closed circles, so these are both going to have brackets. Okay, and then next for the range we're going to scan bottom to top, and it starts existing right here, which is y equals 0, and then it goes until right here once again, which is y equals 3. So it goes from 0 to 3. Both of these are closed filled in circles, so they have brackets. So 0 to 3 for the range. Okay, and the next one here for B, taking a look at the domain. The domain, scanning it left to right, it starts right here at -3. It ends right here at +2. So it's -3 to +2. However, at -3, there's an open circle, so that gets a parenthesis. 2 is a filled in circle, so that gets a bracket. Okay, and next for the range, we're going to scan this bottom to top. So it starts here at y equals 1, and it ends here at y equals 2. So it goes from 1 to 2, and once again, it has a parenthesis and a bracket. Okay, and now for C, finding the domain first and scanning it left to right. So it starts right here at x equals -2, and then it goes right here until x equals 1. So this is going to be -2 to 1, and it has a filled in circle for -2 and an open circle at +1. So bracket on the -2 and parenthesis on the +1. Okay, now next for the range. The range, the function actually starts right here, and that's at y equals 1. And it goes up to right here, which is y equals 5. So it goes from 1 to 5. The 5 has a bracket on it because it's closed circle. At y equals 1 here, since it's cutting through, that is actually the same thing as a closed filled in circle. So that is a bracket. So if it's cutting through at one of the endpoints, that's the same as a filled in circle, and that is a bracket. Okay, and the next one for D, taking a look at the domain. Domain scanning left to right. So this one's a little different. We actually have an arrow here. Since it's an arrow to the left, that means it's going to be from negative infinity with a parenthesis, and then it stops over here at x equals 4. So it's negative infinity to 4, and it's going to have a bracket on the 4 because it's a filled in circle. Next, for the range, we go bottom to top. So it starts right here. That's at y equals 0. And there's an arrow. Even though the arrow doesn't seem to be going up, it is going up. We don't care about the left or right direction. We just care about the up or down direction here. It is still going up. So that's actually going to positive infinity. So the infinity gets a parenthesis. We get a bracket on the 0 because it was the filled in circle. So that is the domain and range for that example. Okay, now for these two down here for letter E for the domain. Domain left to right. It starts right here and ends right here. And that looks like it goes from -2 to +2 in terms of the x values. And they're both going to get brackets because they're both cutting through those points. Next for the range bottom to top. So for bottom to top for the range, it's going to start right here and end right here. We're looking at the y values. That's going to be -2 to -2 with brackets. So the domain and range happen to be the same for this one. Okay, and then the last one for F, finding the domain. Domain scanning left to right. So notice that there's arrows on both ends here. So we don't care about the downward direction, we just care about the left or right direction. The one on the left, it seems to be going a little bit to the left as it's going down, which means it's going to be negative infinity. And the one on the right seems to be going to the right still, so positive infinity. So the domain is negative infinity to positive infinity. And for the range, bottom to top. So hopefully it's pretty obvious that it's coming from negative infinity. And we keep going until it stops, and it stops up here at y equals 4. So the range is negative infinity to 4. And once again, it's cutting through that point, so we get a bracket for the 4 end point. Okay, so that is it for this chapter.